Okay, up until this point in your differentiation education, you've only differentiated functions that are y equals a function of x. This is called an explicit definition for y, okay, because y is defined explicitly in terms of x. However, not all equations have y as a function of x or can make y the subject. So more generally, we have a function of x and y equals either another function of x and y, or maybe a constant, or set it to 0, because we can always minus that across the other side and combine it into this. And this definition of our curve is called an implicit definition. Now, to differentiate such a function, we have to use implicit differentiation to get dy by dx. And typically for these types of questions, it is common for dy by dx to be some function of x and y, different to f, so let's call it g. Okay. So we end up with a function of x and y in terms of the definition of dy by dx. So you need to know the exact coordinate, x coordinate and y coordinate, to plug in to find the gradient at that point. Okay. Now, reversing this process to go from this back to that again, that is something called solving a differential equation, and that is something that we will study at the end of the integration chapter. Back to this definition, the implicit definition. You have met a function in year 12 that looks like this, namely the circle. X squared plus y squared equals r squared. You can't make y the subject of this, or if you can, you'll have a little plus minus kicking around, which isn't then a function. It's a mapping, because you have one input for multiple outputs. Or more generally, there we go. This is a circle with a centre AB, with a radius r, and we can see I've rearranged it to make it equal to 0. So this would be our definition of f of x, y. F of x, y. Okay. All right, so what do some of these graphs look like? Well, we know what the circle looks like. Here we go, there's one circle for you. And this is a circle of radius 2. But with implicit curves, we can get some kind of wacky functions coming out. So we might have something that looks like this. And we can see, because y is no longer the subject, it doesn't have to be a function. Okay, you plug in one x value, you get multiple y values out. And if we plug in multiple, if we're looking for one y value, we can see that multiple x values give the same thing. So back to function theory, this is a many-to-many mapping. Or maybe we might have a loop. Or maybe we have something that looks like that, where the gradient becomes infinite at these points, or 0 at this point. Or maybe we have something that looks like that. We don't know what these graphs necessarily look like, and they're really hard to sketch, but it's rare that you're asked to sketch these on an A-level course. We're just asked to differentiate them. Okay. So let's have a look at an example question, and how do we go about doing it? So we've got a curve C. It's defined as 20 sine x plus 2y squared plus 5y cubed minus 10x minus 4 equals 0. And we're told to find the coordinates of the turning point with the smallest positive x coordinate. So what we want to do with this is we want to take that equation and we want to apply the differential operator d by dx. Okay, so that's an operation, just like perhaps like the square root function or the squared function. We're applying this operation to both sides of the equation. Now this is a linear operator, which means we can apply this to each term in that line. So we're going to have d by dx of 20 sine x plus d by dx of 2y squared plus d by dx of 5y cubed plus d by dx of minus 10x plus d by dx of minus 4. And that's going to equal d by dx of 0. Now, all this d by dx means is you're going to differentiate the contents of each bracket with respect to x. That's all that means. So, some of these we can do straight away. So, we've seen how to differentiate 20 sine x with respect to x. So, if we take that, then we can say that this is just going to be 20 times the cosine of x. Nice and straightforward. This one, however, is a little bit trickier because we're trying to differentiate a function of y with respect to x. So, how do we go about doing that? Well, we use implicit differentiation, which is really just an application of the chain rule. So I'm going to say I'm not going to differentiate with respect to x because I've got no idea how to do that. Instead, I'm going to differentiate with respect to y, that function, which is 2y squared. And then to correct that, I'm going to times that by dx, by dy by dx. So that if you look at it as a fraction, the dy's will cancel and we're left with d by dx, which is exactly what I wanted. But now I'm differentiating the 2y squared with respect to y instead of differentiating it with respect to x. So the 2y squared will differentiate to 4y, so that'll be 4y, and I need to times it by dy by dx. So it's going to be plus, I'll do this bit in red, 4y times dy by dx. And we can do the same thing here. I don't want to differentiate that with respect to x because I don't know how to do that. But if I differentiate it with respect to y and times it by dy by dx, I will get the right term. So if I differentiate this with respect to y, that's going to be 15y squared. And then I need to times it by dy by dx. And the other three terms are nice and straightforward. The minus 10x will differentiate to minus 10, the minus 4 will go to 0, and the 0 remains at 0. There we go. So that is implicit differentiation in action. And we've done the same thing here as we did to the first term. We differentiate it with respect to y. So we differentiate 5y cubed with respect to y and times it by dy by dx. And that gives us this term. Now we've got this line, we can make dy by dx the subject. dy by dx then is going to be equal to 10, subtract 20 cos x, all divided by 4y plus 15y squared. There we go. That is dy by dx. And we can see that dy by dx here is a function of x and y. Okay, and that's, as I said earlier, is not uncommon. Let's go back to the question. Find the coordinates of the turning point with the smallest positive x coordinate. Okay, so year 12 knowledge, turning point, that implies, usually, not always though, that dy by dx is equal to 0. So if we want dy by dx to equal to 0, then we're going to want 10 minus 20 times the cosine of x to equal 0. As long as the bottom is not 0 as well, but we can check that once we get a y coordinate. That implies that cos x is going to be a half. And then that implies that x is going to be pi on 3. That's the smallest positive x value that satisfies cos x equals a half. Okay, so that gives me my x coordinate. Now if I take that x coordinate and I plug it back into the original curve, then that will give me my an equation for y. Plug that back in. It was 20 sine x, so that's 20 times the sine of pi on 3, plus 2y squared, plus 5y cubed, minus 10x, but x was pi on 3, minus 4, equals 0. So this is now a cubic equation in y. So, best way to solve a cubic is to go into equation mode on the calculator. It is a polynomial of order 3, and the coefficients are 5 for y cubed, 2 for y squared, and then nothing for y, there's no coefficient of y in there. And then the constant is going to be 20 sine of pi on 3. Now I'm in degrees mode. Should have checked that before. So I'm just going to convert that to degrees. So times 180 on pi. So I could have just put in 60. Minus 10 times pi on 3. So minus 10 pi on 3. And then minus 4. Okay. There we go. So it's got my coefficients of y, and if I execute that, we can see that there are 2 complex roots and 1 real root. So it's the real root I want. So minus 0.986. If I plug that in, my coordinate then is going to be pi on 3 minus 0.986. And that's the coordinate of my turning point. Okay. And we can get the graph of that up. That was one of the 5 graphs I showed you at the beginning. And the coordinate of this point here is actually, it is pi on 3, and then it's slightly above minus 1. It's minus 0.986. So that's the first one. Okay, example number 2. Find an expression for dy by dx for the circle x squared plus y squared equals r squared. So we're going to apply exactly the same thing again. This is an implicit definition of a curve. So we're going to differentiate implicitly. So d by dx of x squared plus d by dx of y squared is going to equal d by dx of r squared. Okay. So this one's nice and easy. That one is just 2x. That's a nice year 12 one. This one we're going to need to apply our chain rule, or the implicit differentiation technique, which we're doing now. And that's going to equal the differential of a constant. R is a constant with respect to x. When we differentiate a constant, it goes to 0. Okay, so we've just got this to deal with. Differentiate y squared with respect to y. That is just 2y times y prime. That's still 2x over there. That's still a 0 over there. And now make dy by dx the subject. Well, I can divide the whole thing by 2, subtract the x, divide by y. I get that dy by dx is equal to minus x divided by y. That's the answer. That is an expression for dy by dx for that circle. There we go. And notice that it's the same derivative independent of what the radius is. Okay, so it's always the same differential function. Okay, example number 3. Find the coordinates of the turning point of this curve. All right, so we are going to apply again our differentiation operation to both sides of this equation. So I want to differentiate with respect to x squared y, and then want to differentiate with respect to x, y squared, and then that's going to equal the differential with respect to x of x. Okay. Now, second term, this is, I'll come back to the first one in a minute. The second term is nice and straightforward now because we've seen a few of these. It's the differential with respect to y of y squared times dy by dx. That's our little chain rule. That's going to equal the differential of x with respect to x, which is 1. We know that from year 12. Now, this is the new bit for this question. What goes here? How does that differentiate? We have x squared times y. Well, x squared times y is a product. So let's bring it down here and let's apply the product rule. So we can see the product rule may play a part in some of these questions. So let's say u equals x squared and v equals y. Okay, so we can see that what we're trying to differentiate is the product of u and v, x squared times y. Differential of u with respect to x, so I'm going to write this as du by dx, that is 2x. And the differential of v with respect to x, well, in this case, is just dy by dx. Just differentiating both sides with respect to x. If this was a more complicated expression for y, then you'd need to employ implicit differentiation here. Okay, so we can now use the product rule to state what this question mark is, the differential. Now, the product rule says that the differential of uv is equal to uv dashed plus vu dashed. So we're going to end up with x squared times dy by dx plus 2xy. Okay. So that is the question mark. Then we have this, which is going to be an implicit differentiation, but we've already split it out, so that's just going to be a 2y times dy by dx. And we already know that this whole thing equals the number 1. So now from here, now that we've differentiated all of the terms in our original equation, we can apply the differential, we can make the differentiation term the subject of this. So we're going to end up with dy by dx is equal to 1, subtract 2xy, divided by the coefficient of dy by dx, which is x squared plus 2y. That is the derivative, that is dy by dx for this, curve. Okay, back to the question. Find the coordinates of the turning point of the curve. It says the turning point. That does imply there is only one turning point. So, for the turning point, we want y prime to equal 0, usually. That means that 1 minus 2xy is going to equal 0. This implies that 2xy equals 1. Okay, so the turning point satisfies this equation. But, and this is the key part here, the turning point is also a point on the curve. So therefore the turning point must also satisfy this equation, because it lies on the curve, and satisfies this equation because we want y prime to be 0. So we need to solve those two simultaneously. And this is not uncommon for these types of question. So x squared y plus 2y squared equals x. And let's say y is going to be equal to 1 over 2x. So we're going to take this definition of y from here, and we're going to plug it in to the original curve. Okay, so dy by dx equals 0 gives me that y is that. Plug that into there. That's going to give me x squared times 1 over 2x, so that's a half x, plus 2y squared, so y squared is going to be 1 over 4x squared, so that's going to be plus 1 over 2x to the minus 2. Okay, 2 times the quarter will give me the half, and the y squared, that's x to the minus 2. That's going to equal x, and that gives me a nice polynomial in x. So I'll just go ahead and solve that. If I times it all by 2x, I'm going to get x squared, times it all by 2x squared. That's going to give me x cubed plus 1 equals 2x cubed. So x cubed is going to equal 1. Okay, subtract that across. I'm only looking for real solutions, so therefore x equals 1. And then I can plug that back into either this one or this one to find a number for y, which is going to be y is half. So the coordinates then of the turning point are 1 half. And we can see that on the graph. Okay, this is the graph. This is this one that we had earlier. And turning point is here, which has x coordinate 1 and y coordinate half. Obviously you don't have access to something like this in an exam. Even graphical calculators can't sketch implicit curves. But we can see on the tablet that is looking about right. And that's the only turning point. Okay, next example, which I think is my last one. Oh no, I've got two more. Okay, find the equations of the tangent and the normal to this curve at the point 1, 2. Okay, so it's not used the word definition, it's not used the word differentiation anywhere in the question, but it's used the word tangent and the word normal. And such should immediately take you to differentiation in your head, because we need the gradient of the curve at the point to find these two lines. So let's differentiate. We're going to differentiate with respect to x, both sides of the equation. And what I'm going to do is I'm going to multiply out this bracket here, so it's going to be 5x squared minus x cubed. Okay. So we need the implicit differentiation definition to differentiate this, so d by dy of y squared times dy by dx. That's going to equal the differential of 5x squared with respect to x, which is 10x, minus 3x squared. Now we can apply this to give us 2y times dy by dx. That's still going to equal 10x minus 3x squared. And now we can make dy by dx the subject. So y prime or dy by dx is going to be 10x minus 3x squared, all divided by 2y. Okay, so there's my derivative. Now, find the equation of the tangent and the normal to the curve at the point 1, 2. So that implies that 1, 2 lies on the curve. You could check it. If I plug in x as 1, we should get equals 4. But you don't have to. The question implies that it is indeed on the curve. So I'm going to take x equals 1 and y equals 2 and plug it into the derivative to give me the value of dy by dx at the point I'm interested in. So y primed at the point 1, 2 is going to be equal to 10 minus 3 divided by 6. That's like divided by 4. Okay, so 10 minus 3, okay, plugging in x is 1 into the top, divided by 4. Okay, plugging in y is 2 into the bottom, so that's going to be 7 quarters. So the gradient of the curve at my point in question is 7 quarters, or 1.75. So I just need to find the equation of the linear line that has that gradient that goes to that point. Now that would be my tangent. And then I need to find the equation of the linear line that has the negative reciprocal gradient of that goes to that point. And that will be the normal. So let's do each of those separately. Let's have a look at the tangent. We wanted to go through the point 1, 2. So y minus 2 is going to equal m times x minus x1. And that will give you y is equal to 7 quarters x. And then we've got minus 7 quarters plus 2. Or if you like, minus 7 quarters plus 8 quarters is just plus a quarter. Okay. So you could leave it like that. The question's not asked for a particular form. So we could leave it like that, or you could tidy it up and say, let's go with 7x minus 4y plus 1 equals 0. So there we go, that's the equation of the tangent. Okay, the normal is going to be exactly the same process, except the gradient is going to be the negative reciprocal. So I'm going to get y minus 2 is going to be equal to minus 4/7 of x minus 1. Again, making y the subject, that's going to be minus 4/7 x. And then here I'm going to get positive 4/7 plus 2, or if you like, positive 4/7 plus 14/7. It's going to be plus 18/7. Okay. Again, you could leave it like that, or you could tidy it up. And I'm going to say 4x plus 7y minus 18 equals 0. So I brought those two across the other side this time. Okay. And one final example then. Find the coordinate of the point on the curve where the gradient is infinite. Okay, so again, it's used the word gradient, so you should immediately be thinking, okay, differentiation. So apply differentiation to this. We're going to get 2x differentiates to 2. Y squared is going to differentiate to 2y times dy by dx. The 1 disappears, and now this we're going to need the product rule for. So I'm just going to apply the product rule here, and then that's going to equal 0. Now applying the product rule, let's say u equals x squared and v equals y squared. Then du by dx, again just a year 12 differential, is 2x. And dv by dx, well, we're going to need to use implicit differentiation here. I can't differentiate that with respect to x as it is, so I'm going to differentiate it with respect to y, so it's 2y, and I'm going to times it by dy by dx to correct it, so times by dy by dx. Okay, so there's my derivative of v with respect to x. And now the product rule says that the differential of the product uv is equal to uv primed plus v u primed. So that's going to be 2x squared y times y prime. Okay, so that's that times that. Plus vu prime, that's going to be 2xy squared. Okay, so that's the bit that's going to go in that question mark bit there, although it will be a negative. Okay, so that gives me this equation, 2 plus 2y times dy by dx minus this, so that's going to be 2x squared y times dy by dx minus 2xy squared, and that equals 0. Okay, so that's applied the differential operation to both sides of the equation, and now we're going to make dy by dx the subject. So dy by dx, that's going to equal 2xy squared minus 2. Okay, so I brought that across, and I brought that across, and I need to divide by the coefficient of y primed, so that's 2y minus 2x squared y, and then we can divide top and bottom by 2 there, so that's x y squared minus 1 divided by y minus x squared y. There we go, that's the derivative. Now back to the question. Find the coordinate of the point on the curve where the gradient is infinite. Now we don't have an infinite gradient in explicit differentiation, but in implicit differentiation this is possible. So an infinite gradient, that occurs when the bottom is going to be 0. So infinite gradient, so put that in quotes, infinite gradient, that implies in this case that y minus x squared y equals 0, which means that either y is 0 or x squared is 1. So either y equals 0 or x squared is 1. Okay, so we've got 3 values there. We've got y is 0 to plug in, or we've got x is 1 to plug in, or we've got x is minus 1 to plug in. Now, let's plug them all in separately. Let's see what happens. So plugging in y is 0. If I plug in y is 0 into the original equation, I'm going to get 2x minus 1 equals 0. So that implies x equals a half. So that's going to give me the coordinate a half, 0. Or if I plug in x is 1, if I plug in x is 1 into here, I'm going to get 2 minus 1 is 1. Plus y squared minus y squared, because x is 1. So that's just nothing, and that equals 0. So I get 1 equals 0. Oh, no, 1 doesn't equal 0. There's no values of y which satisfy that equation, so that's not going to produce anything. And the other one was x equals minus 1. So if I plug in x is minus 1 into here, I'm going to get minus 2 minus 1. That's minus 3. And plug in x is minus 1. I'm going to get y squared minus y squared again. So again, they're going to disappear, and that's going to equal 0. Again, there's no solutions there because there's no values of y which make that equation true. So there are no solutions. So therefore, the only coordinate is a half, 0. That's the only point where the gradient is infinite. And if we look at the graph of this one, I'll zoom out a little bit. There we go. This was this curve, and we can see that indeed the gradient here is infinite. And what's happened at x is 1 is we have a vertical asymptote. So that you can't evaluate the function at 1. It doesn't have any y values when x is 1. And the same thing occurs when x is minus 1. We've got another vertical asymptote here when x is minus 1. So we can't find any point on the curve where the gradient is actually infinite when x equals minus 1. But the gradient is infinite here when y is 0, and that was when x was a half. And that is our infinite point. Okay, it's quite a long video, but I hope there's lots in there to keep you going. If you have any questions, drop them in the comments and I'll get back to you when I can. Thanks for watching.